Hello again. This is video lecture 17.3, and we're going to talk about section 3, chapter 17, interference, specifically interference of sound waves. Now, we talked about the phenomenon of interference for the first time in chapter 16, where we said interference is what you have when you have two or more waves in the same medium at the same time. And there we were looking specifically at two waves on a stretched string at the same time. And we found that you could get a range of outcomes for the net wave that you would observe when you had the two waves on the same string. And that range extended from the biggest possible amplitude you could get, which was twice the amplitude of the individual waves, assuming they have the same amplitude. That's called fully constructive interference. All the way down to zero amplitude for the net wave, fully destructive interference. And we're going to talk about the same phenomenon now, except we're talking about sound waves, not waves on a string. And generally speaking, in the everyday world, when we have sources of sound waves, the sound waves are traveling outward in the everyday world, three-dimensional space, not one-dimensional space. So the geometry is a little bit more complicated now, but the idea is still basically the same. We have two sound waves in the same medium, air, for example, at the same time. What kind of sound wave will we observe, detect? A very large amplitude sound wave, if you like, loud, or basically no amplitude sound wave, quiet. That would be fully constructive interference down to fully destructive interference. So here's the kind of geometry we're going to focus on in this section of chapter 17. Here's the scenario we're going to imagine. We have two sound waves with identical wavelengths, just to make things a little bit less complicated, passing through a common point in space. Okay? And when you have two waves at the same point in the medium at the same time, you have interference. Okay? Now, what we're saying here is that the kind of interference that we observe at the point depends on what we call the phase difference phi between the two waves. And remember, phi is basically telling you, if you think of two sinusoidal curves, how are they lined up with each other? Are they lined up crest to crest, or are they shifted relative to each other? Okay? Okay. We will assume in this picture that the sources of the sound waves are what are said to be in phase with each other. Okay, so we have to have two sources of sound waves. If you like, two speakers, right? Two audio speakers. And we'll assume these are the kind of speakers, you can get these, that emit their sound uniformly in all directions. Spherically symmetric speakers. And this picture that we're drawing here shows those two sources. They're labeled here S1 and S2. And they're represented as dots in this image. But you're to think of those as spherically symmetric speakers, emitting sound waves out in all directions, each of them. Okay? And we're going to assume, it doesn't have to always be this way, by the way, but let's assume for now that the two sources are in phase with each other. What does that mean? That means that the sound waves emitted from S1 are exactly lined up with the sound waves emitted from S2. When the pressure wave in S1 that's coming out of S1 is a maximum, the pressure wave coming out of S2 is also a maximum. Okay? Now they're emitting these sound waves out in all directions. So if I draw, they'll be circular in this two-dimensional view, the wave fronts for each source that are propagating outward at any given time, you would just draw circles centered around each source. Those would be the wave fronts. And then you have to visualize, as time goes on, that those just spread outward, like ripples on a pond of water. Okay? All right, so that's the part of the geometry here. Two spherically symmetric sources of sound, S1 and S2, in phase with each other. And we've drawn a line there just along them for visual reference. And another important thing is how far apart they are from each other. We'll call that distance D. All right, so those sound waves are traveling outward from S1, and they're traveling outward from S2. And so in the medium, the air that's surrounding, as we look down on this from above on this situation, let's look out here at this point P that is drawn right here. A little bit cut off there. That's a point in the medium, a point in the air. What kind of sound wave will be detected there? Well, I've got two sound waves at point P, so I have to combine them to get the net sound wave. And I just basically want to know, will I have fully constructive interference? Will it be loud at point P? Fully destructive interference? Will it be quiet at point P? Or anything else called, that would be intermediate interference. And so that kind of interference between the two sound waves at point P boils down to finding the phase difference phi between the two waves arriving at point P. The two sound waves arriving at point P. What's the phase difference between them? Are they lined up crest to crest, or are they shifted relative to each other? And why would there be a phase difference at all between the two sound waves at point P, given that they leave the sources in phase? If they leave the sources S1 and S2 in phase, wouldn't they be in phase at point P? And the answer is not necessarily. Because the two waves, if you go in a straight line from S1 to P, travels a distance L1. That's labeled right there. That's an L1. And the wave in a straight line from S2 to P travels a distance L2. And if those distances are different, then that can cause the waves to be shifted from each other when you look at point P. Okay? And the fact that those differences in distance that they travel, L1 and L2, to get to point P, that's called a path length difference. So what we're saying is that you can get a phase difference between the two waves at point P merely from a difference in distance traveled from the respective source to point P, a path length difference. We're going to assume, even though this picture doesn't really imply it very well, that the two distances L1 and L2 are both quite large compared to the distance D between the sources. That way, the two, if you like, the two rays of length L1 and L2 that are converging at point P are nearly parallel to each other. That ends up avoiding some mathematical complications that we just don't really need to deal with right now. Nevertheless, I'm going to now tell you the most important relationship we need to know for this section. Remember, all I really want to be able to do is tell you at point P, is it going to be fully constructive interference, loud, fully destructive interference, quiet, or intermediate interference, something in between. And all you need is the little relationship that I actually more or less derived for you in chapter 16 when we studied interference of waves on a string. Okay? And so I'm just going to go to that right now and remind you of it. It's this relationship right here, and it's very important when you look at interference of waves. And it says, the phase difference, phi, let me write that, the phase difference, phi, in radians, divided by 2 pi radians, so phi over 2 pi is dimensionless, is equal to the path length difference, path length difference, delta L, that would be in SI in meters, divided by the wavelength in meters. Again, the ratio is dimensionless. Okay? So phase difference phi in radians over 2 pi equals path length difference, we'll call that delta L, in meters over the wavelength in meters. Delta L, as I said, is the path length difference of the two waves, which I will write as absolute value of L2 minus L1, meaning I don't care which one's the longer, L2 or L1, generally speaking. I just need the absolute value of the difference. Okay, here's another thing we said in chapter 16. When do you get fully constructive interference between two waves? The answer is easy. When the phase difference phi between the two waves is an even integer times pi. So we write it like that. Phi equals 2m pi, where m can be any number in this string of integers, 0, 1, 2, 3, dot, dot, dot. Because if m is any integer in that string, 0, 1, 2, 3, dot, 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 then 2m pi would be, well, it could be 0, 2 pi, 4 pi, 6 pi, 8 pi, 10 pi, dot, dot, dot. Then you'll get fully constructive interference. Big amplitude sound wave, it'll be loud at point P. Okay? Now, use our little relationship between phi and delta L. That is to say, let's substitute that phi, let me write that right here, equals 2 pi times delta L over lambda. And put that right there where the phi is. The 2 pi's will cancel, and you'll get this relationship right here. That the path length difference divided by the wavelength must be the integer m. Not just an even integer, any integer m. We're not allowing negative integers because we've defined delta L to be positive. So note, what I'm saying to you is this condition for fully constructive interference is exactly equivalent to that one. They're saying the same thing. That the two waves, when they meet at point P, will be lined up in phase, crest to crest. That will happen whenever their phase difference is an even integer multiple of pi in radians, or their path length difference, delta L, is an integer multiple of the wavelength, right? Because you can write that like this, that second condition, delta L equals m times lambda. All right, that's for fully constructive interference at point P. Now what about fully destructive interference, the other extreme? Well, then I need the waves to be lined up at point P, crest to trough, exactly, crest to trough, so that I get fully destructive interference and I get no amplitude for the net wave. And the sound will be quiet, the sound wave will be nil. The condition there is that the phase difference phi in radians must be, notice how we're going to write it, 2m plus 1 quantity times pi, where m can be, again, any integer in that string, 0, 1, 2, 3, dot, dot, dot. So what does that mean? Well, just start with m equals 0. That would mean phi equals pi radians. If m equals 1, then phi equals 3 pi radians. If m equals 2, then phi equals 5 pi radians. So here, to get fully destructive interference, we need the phase difference phi to be an odd integer multiple of pi. Pi, 3 pi, 5 pi, 7 pi, 9 pi, dot, dot, dot. And you'll get fully destructive interference at point P. Again, do that substitution for phi, 2 pi times delta L over lambda, and divide out the pi's, and divide both sides by 2, and you will get this expression right here. Delta L over lambda for fully destructive interference must be m, one of those numbers in that string of integers, plus a half. So if m is 0, then delta L over lambda is 1/2. If m is 1, it's 1 1/2, 3/2. If m is 2, it's 2 1/2, 5/2, etc. Okay? So you can rearrange that if you want and write it delta L equals m plus 1/2 times lambda. And that's will get you fully destructive interference. So this way to write the expression for fully destructive interference, that the phase difference in radians must be an odd integer times pi, is equivalent to that expression. That the path length difference over lambda must be an integer plus 1/2. Those are the main things we have to be able to do. Use those expressions to see if we're going to have fully constructive, fully destructive, and if it doesn't fit, if you don't have a phi that satisfies either one of those, or a delta L over lambda that satisfies either one of those, that is to say any other value of phi, gives you what's called intermediate interference. All right, I want to show you some pictures now to try to help you visualize the kind of interference pattern you'll see. Well, here, I guess is what I should say, with the sound waves in this kind of situation. And I'm going to do a combination of the static image that I'm showing you now, a photograph of a real interference pattern in 2 dimensions, and an animation on Wiley+. Let me start with the static image. And what we're going to show you is what's called a 2-source interference pattern. Let me try to set the stage here. It's equivalent to the picture I just showed you up above, where I have 2 spherically symmetric sources of waves, S1 and S2, and we've just drawn a line between them to visualize the line connecting them. And that line was kind of up and down in the plane of the image. And all I've done in this picture, in this animation, is rotate the line connecting the sources by 90 degrees. Let me explain. We've got an XY coordinate system, X and Y are in meters, and I've got 2 spherically symmetric sources of waves. They're represented here by red dots, there and there. So they're sitting on the x-axis, and the line connecting them would be the x-axis. And they're emitting waves, spherically symmetric outward from each, the sources are assumed to be in phase with each other. And the animation allows us to select the wavelength of the waves they're emitting, lambda, and right now that's 0.5 meters. Okay, now, there's a certain distance between the 2 sources on the x-axis. And we'll call that d again. We happen to use capital D. And in this particular animation, that distance d is 1 meter. The 2 sources are 1 meter apart. That distance d is right there. Okay? That's the distance along the x-axis that they are separated from each other. Okay, so they are fixed at a separation d of 1 meter. The default wavelength, lambda, is 0.5 meters. So, let's just note, we have a situation where the distance between the 2 sources, d, happens to equal 2 times the wavelength of the waves that they are emitting. So what would you observe for the kind of interference pattern that these 2 sources of waves produce? Okay, now the image, let me explain what it's trying to show you. First of all, if I've been talking about sound waves, hear would be the word, right? What do you hear? But it's easier to see sometimes than to hear. So we need an image that we can visualize, a pattern that we can visualize. So what I want you to think about, because the physics will be basically the same, is as if this were a square tank of water. In fact, you can buy these things. They're called ripple tanks. It doesn't have to be a very deep tank of water, maybe just a few centimeters, okay? But it's a square tank, and it's got water in it a few centimeters deep. And it's got little mechanical plungers that you put in position, and you can control, and you can make them then go up and down and disturb the water, like bobbers, like that. And you can have them in phase, or you can even set them up to be out of phase if you want, okay? Well, we'll assume they're in phase, like this. What will those bobbers do, those plungers, as they go in and out of the water? They will produce water waves. and the water waves will ripple outward, circularly, symmetrically from each source, and I'll have two water waves in the medium at the same time, so I'll have interference. And at certain places, I should get fully constructive interference, where the amplitude of the water wave, the up and down, would be very large. And in certain places in the ripple tank, I should get fully destructive interference, where there's basically no up and down amplitude of the water. And you can actually make these water wave interference patterns. And I want to show you, and that's, by the way, that's what this drawing is. This animation. It's an image from an animation. Because the regions where you see pretty sharp rings of blue and white, those are supposed to make you think of the ripples of the water going up and down, large amplitude, fully constructive interference. The regions that look a bit blurry, that's supposed to make you think of no up and down motion of the water in there, fully destructive interference. And so you see these regions where you got fully constructive interference with large amplitude up and down, and fully destructive interference with essentially no amplitude up and down. And if you're skeptical that that really happens, now let me show you a photograph in real life. This photograph was taken, I'm acknowledging the source here, from the Veritasium YouTube channel, excellent science YouTube channel. You should check it out. Okay? And what the creator here did, a very creative person, took two basically bobbers on a little pond. They're just outside the field of view down at the bottom, and is bobbing them up and down in phase with each other on an actual pond of water. This is real. It's a photograph of a real pond of water. And then let the interference pattern develop. And I think you can see, right, that along lines like there, you've got very distinct bright and dark, bright and dark. That's high amplitude. The bright are the crests that's hitting the light. The dark are the troughs that are hidden from the light. But it's very clear distinction, bright, dark, bright, dark. High amplitude, up and down. Fully constructive interference, FC. That would be true along that line. That would be true along that line. That would be true along that line, and so forth. All lines of fully constructive interference. If you want to be really fancy, they're called anti-nodal lines. That's one example right there. Anti-nodes. Okay? Now, then you also see lines like right around through there, and there, and there, and there's one here too, where it just looks blurry, like there's not much distinction at all along that line between bright and dark. That's because that area of the water isn't moving up and down. Okay? So there you have fully destructive interference. Those are called nodal lines. Okay? So this really does happen. And so the animation image I'm showing you up above is a representation of exactly this kind of physics. And we call this, the whole big picture, an interference pattern. So now let's go back to that. Okay? Because I want to study that pattern in some detail. All right? You see what I'm talking about? You've got regions of antinodal lines and nodal lines. Antinodal lines are fully constructive interference, big amplitude up and down. That's right along the center of any region that has very distinct blue and white pattern. And nodal lines, fully destructive interference along any region that's blurry. So for example, here is an antinodal line, bisecting, if you like, the line between the sources. Okay? I'll mark that one. Antinodal line. I want to understand why that's an antinodal line. Okay? All right, so I'm going to focus on the antinodal line there, and then we're going to look at some of the other ones, some of the other antinodal lines. But let's start at the first one, the one I just drew. And let me pick a point somewhere out there, kind of far away from the sources. Just marked it there with an X. And let me label that point A. So at point A, I want to understand why that's an antinodal line. Antinodal means fully constructive interference. Well, let's just remember the condition for fully constructive interference in our pattern. Okay? We need the path length difference, delta L, to be an integer multiple of the wavelength, m times lambda, where m is a number in that sequence of integers, starting at 0 and going up. Let's see why A is a antinodal line. I contend that at point A, the path length difference, delta L, is very easy to determine. Can you tell what it is? What's the path length difference for the rays from the sources going from the two sources to point A? Understand what I'm saying? There's one ray from source 1. There's the other ray from source 2. L1 and L2. What's the difference between L1 and L2 for that line that bisects the middle there? Well, the delta L is 0, right? Because they travel the same distance from each source to point A. There is no path length difference on that bisecting line. So delta L is 0. Well, that's fine. That satisfies the condition for fully constructive interference. 0 path length difference. Yep, it's going to be fully constructive. So that's why that point A is on an antinodal line. Let's look at another antinodal line. Let me pick another point. I'm going to pick one over here to the right. I'm going to label that point C. I'm going to do that one next, actually. At point C, let's see if we can figure out the path length difference. Now I'm talking about, let me get that A back in there. I'm talking about that path length from source 1 and that path length from source 2. Can you see what the path length difference is? Did you say it's just the distance d between the two? Because the one wave has to travel that one extra distance, d. Okay? So the path length difference is d. And it just so happens, in this case, that the path length difference equals 2 times the wavelength. Let me write that a little bit more neatly. Okay? Okay, but a delta L of 2 lambda, an integer times the wavelength, satisfies the condition for fully constructive interference. So that explains why the point C over there is an antinodal line. It's on an antinodal line. Notice it's in the middle of a region that's clearly fully constructive interference. Now, in the first quadrant of the XY coordinate system, up in the upper right, do you see the other remaining antinodal line? You see it's going right up in here, right up through there. So let me pick a point somewhere out there along that one and label it B. And now let me talk about what the path length difference must be at point B. Now this one we're going to have to infer, because we're not going to do any complicated calculation. But let's note, at point A, the path length difference was 0, or 0 times lambda. At point C, over there to the right, it was 2 lambda. I contend when you're to the right or to the left. Directly to the right or the left of either source, that's the biggest path length difference you can get. And and that's point C. So if that path length difference is 2 lambda, and the path length difference at point A is 0, what do you think the path length difference at point B is? Did you just say 1 times lambda? It's got to be an integer times lambda to be on an antinodal line, fully constructive interference, big amplitude. And and that path length difference is smoothly varying from 0 path length difference at point A to 1 times lambda at point B to 2 times lambda at point C. Now you can keep going around, but you'll come back to the antinodal line where that B is on again if you keep going clockwise around, and that'll be a delta L of lambda. And then you'll get back to the antinodal line going up and down, so that'll be 0. The pattern repeats, is the point. And so we can basically understand where the antinodal lines are in the pattern based on path length difference. But now I want to look at nodal lines, okay? All right, so let me clear out some of my drawings here. Now I want to talk about nodal lines in the picture. Remember, nodal lines are places where we have fully destructive interference. And the condition, or a condition for fully destructive interference, is that the path length difference between the waves must be an integer plus 1/2 times the wavelength, where again, m is an element in this string of integers starting at 0 going up. Notice if I start then with m equals 0 in that formula, the smallest delta L for fully destructive interference is 0.5 times lambda, half of a wavelength. So let's see if we can use this to find out where the nodal lines are. Those are represented in the pattern by blurry regions and dashed yellow lines. So I'm going to mark them, and I'm going to mark the first one we come across right about here. I'm just marking a point on that dashed line, and I'm going to label that point D. So at point D, what must be the path length difference? I'm going to infer it. I'm not going to do a detailed calculation. Again, at point A, which was over here, we had a delta L of 0. At point B, at point B, which was here, we had a delta L of lambda. Point D is roughly in between A and B, so it shouldn't seem too surprising. Remember, it's also got to be a nodal line. When I say that the delta L along the line that's got point D on it is 0.5 times lambda, because that will satisfy this condition for fully destructive interference. Notice in the first quadrant of this diagram, there's another yellow dashed line in a blurred region, fully destructive interference. And let me pick a point on that. That's another nodal line. Oops, let me use, pardon me, the lighter green, right about there. And let me label that point E. Remember, this point down here is C. Then I've got all my points back again. What do you think the path length difference is at point E on that other nodal line? What is the delta L? You have a guess? Point E, right here. Did you say 1.5 times lambda? Because it's got to satisfy the condition for fully destructive interference. And the whole path length difference smoothly increases as we go from the points A to D to B to E to C, with a delta L ranging from, respectively, 0 to 0.5 lambda, to 1 lambda, to 1.5 lambda to 2 lambda. Right? 0 lambda, 0.5 lambda, 1 lambda, 1.5 lambda, 2 lambda. Okay? And that's as far as you can go in terms of the delta L. You can't get any bigger than 2 lambda for this wavelength. Okay? Just like the water interference pattern I showed you in the photograph. All right, now what I'm going to talk about, I'm going to ask another question now. I'll write it down over here. I'm going to be going here in a moment to a Wiley Plus animation of this exact image. And in that animation, I can adjust the wavelength lambda of the waves emitted by the source, making them smaller than 0.5 meters. So what's going to happen? I'm going to reduce the wavelength. Smaller wavelength of the waves. What do you think is going to happen to the pattern? Now that may be a bit of a stretch, but reducing the wavelength, let's think about it, it's going to basically compress, make things happen on a smaller scale. We're going to be able to see more, we're going to be able to fit more nodal and antinodal lines in this same region of the XY coordinate system. So here's what I'd like to do. I'd like to reduce lambda. I'd like to know what wavelength do I need, right? What lambda gives a new nodal line for the x-axis to the right of the two sources. Okay? So, to the right of the two sources on the x-axis, right now, that's an antinodal line, a region of fully constructive interference. What if I want it to be a nodal line, fully destructive interference, and I'm allowed to vary the wavelength, lambda? What wavelength should I pick? Well, like I said, reducing the wavelength makes the whole pattern compact, and I can fit more nodal and antinodal lines in this same region. And I know that if I want a nodal line, the path length difference must be an integer plus a half times lambda. Now, the biggest path length difference I got so far for fully destructive interference was 1.5 lambda along that dashed yellow line. So the next, to get a new nodal line appearing, I need to go up one more, if you like, notch in the delta L value. Okay? What I need is delta L to equal 2.5 lambda. 2.5. But I want that to be, notice, I want that to be along here. So I'm going to shift the whole pattern a bit. Where now what's happening along the right side, along the x-axis, corresponds to a delta L of not 2 lambda anymore and fully constructive interference, but 2.5 lambda and fully destructive. And I want to calculate the lambda I need. All right, let's see how we're going to do it. So I know I need a delta L of 2.5 lambda, but also, okay, that's the condition for fully destructive interference. I'm also constrained just by the geometry of the situation. That is to say that if I am over there at point C, right, the point C over there to the right, the path length difference, delta L, is simply d, the distance d between the two sources. So those two things have to both be true. Delta L equals 2.5 lambda to get me fully destructive interference, and delta L equals d set by the positioning of the sources. So if I put those two together, I get 2.5 lambda must equal d. Or in other words, lambda must equal d divided by 2.5. Remember, d is 1 meter in this animation. So 1 divided by 2.5, 1 meter divided by 2.5 is 0.4 meters. So if I reduce the wavelength from 0.5 meters down to 0.4, the whole interference pattern should shift a bit, and I should see a nodal line along the x-axis. So now I'm going to transition over to Wiley+, and you can see the same picture on the animation, but the wavelength is now at 0.5 meters. This animation lets me have a lot of sig figs. Now I'm going to just reduce the wavelength to 0.4 meters and hit enter. And I get a new pattern. And you see now the x-axis to the outside of the sources is blurry, is therefore a nodal region, and I have dashed yellow line along that region of the x-axis. So now if I start along the y-axis, the central bisector line, that's a delta L of 0 lambda. Let's just go clockwise around from there. Then I come to the first dashed line, that's a delta L of 0.5 lambda. Keep going to the next antinodal line, that's a delta L of 1 lambda. Next nodal line, delta L of 1.5 lambda. Next antinodal line, delta L of 2 lambda. And then now I'm over on the x-axis with a delta L of 2.5 lambda. And it worked. All right, now let me go back to my notes because I want to do a little more with this. I'm again going to reduce the wavelength. Okay? Now, what I want is I want to reduce the wavelength, and I want to know what lambda gives a new antinodal line, running out of space there, for x greater than or equal to delta over 2. I want another antinodal line. In other words, I want to reduce the wavelength, kind of compress the whole pattern, get more nodal and antinodal lines, and instead of, and I want an antinodal line along the x-axis to the right, but instead of the delta L being 2 lambda, I want it to now be 3 lambda along that x-axis. Okay, so now I want delta L to be 3 lambda for fully constructive interference, and I'm constrained by the geometry over there at point C for delta L to be D, so I need D to equal 3 lambda, so I need lambda to equal D over 3. D is 1 meter, so I need the wavelength now to be 0.333 meters. So now we'll go to the Wiley+ animation, and we'll reduce the wavelength from 0.4 to 0.333. It's pretty sensitive, but there we go. Okay, now we have a new antinodal line going out along X, and the antinodal lines starting on the y-axis correspond to delta L equals 0. Then the next antinodal line is a delta L of 1 lambda. Then the next antinodal line is a delta L of 2 lambda. And then finally a delta L of 3 lambda. And you can keep going with this, right? You could go up and get a new antinodal line along the x-axis. You want to try to calculate what lambda that would be. And what the delta L would be. It would be 3.5 lambda. Or what if the delta L were 4 lambda? You could keep making the wavelength shorter and getting a more and more complicated interference pattern. Okay, and we're going to be doing our class video where we're going to be doing a homework problem that involves this kind of pattern. But the last thing I want to do in this video is just a little bit of practice. We'll just do it together. It's not class engagement, but it's going to get us more practicing with these ideas. Interference of sound waves in air. Okay, we have 2 point sources, S1 and S2 of sound waves. Point sources mean spherically symmetric, like I've been talking about. They are in phase, meaning they emit their sound waves in phase. They are identical sound waves of wavelength 2 meters, right? That's the lambda. see it. All right, now the wording here is a little bit different than I would choose. I took this out of your book, but it is wording that you will hear people say, so we might as well get used to it. Here's the wording. In terms of wavelengths, what is the phase difference between the waves arriving at point P? See the two sources, S1 and S2? See the rays of length L1 and L2 going from the sources to the common point P? We're interested in what is observed at point P. And we're going to start with what they call the phase difference between the waves in terms of wavelengths. And they tell me values for L1 and L2. In part A, L1 is 38 meters and L2 is 34 meters. In part B, L1 is 39 meters and L2 is 36 meters. So first, let's just do part A. All right, let's remember that the wavelength of these sound waves is 2 meters. I'm just going to go to that key relationship I talked about in the first slide, where I call, because I think this is better notation, or more consistent use of language, phase difference is reserved for that symbol phi in radians. And delta L is the path length difference in meters. But that's the relationship between phi and delta L. That's the key thing. Phi over 2 pi equals delta L over lambda. And all I'm really going to do here is get that ratio. Okay? It's not hard to do delta L and divide it by lambda. Now in part A, L1 is 38, so I'm going to do L1 minus L2, and then divide it by lambda, delta L over lambda. 38 meters minus 34 meters means the numerator is 4 meters. The wavelength is 2 meters. The ratio is dimensionless, and it has the simple integer value 2. So I say that's the same thing as saying the path length difference is 2 times lambda. And that's what they mean when they say phase difference in terms of wavelengths. It's what I would call the path length difference. It's 2 lambda. Or to say it another way, delta L over lambda is 2. The path length difference is 2 wavelengths. Some people will call that a phase difference. I would just call it a path length difference. But the point is, you just got to be able to determine what kind of interference you're going to get. Can you tell? What about part B? Just do it again. Do delta L over lambda again. L1 minus L2 over lambda. But now in part B, L1 is 39 meters and L2 is 36 meters. So L1 minus L2 is 3 meters. And the wavelength is 2 meters. Again, the meters cancel. And 3 divided by 2, 1.5. So the path length difference delta L is 1.5 lambda. And that's what I would call the answer. The path length difference is 1.5 wavelengths. That's all. Now part C says, assuming the source separation is much smaller than L1 and L2, what type of interference at P occurs in these two situations? Really, all that what we want you to do is look at those results for delta L in the two cases and tell me, is it fully constructive, fully destructive, or anything else intermediate? Well, if the path length difference is an integer multiple of the wavelength, fully constructive interference. And if the path length difference is an half integer multiple of the wavelength, an odd half integer, like 3/2 lambda, fully destructive. Now, they could have given you a situation where L1 minus L2 over lambda was something like, I don't know, let's say delta L over lambda is 1.9 lambda. No, not 1.9 lambda, beg your pardon, 1.9. Delta L over lambda is 1.9. What would you say the kind of interference would be? Well, it doesn't fit the condition for fully constructive because that ratio has got to exactly be an integer. and it doesn't fit the condition for fully destructive, it's got to be like 1.5 or 0.5 or 2.5 or 3.5. It's neither. So it's intermediate interference. That's what you'd say. You could also say this. It is intermediate, but it's close to 2, right? 1.9 is close to 2. 2 is fully constructive. 1.9 is closer to 2 than it is to 1.5, which would be the fully destructive. So you could say it's intermediate, but closer to fully constructive than to fully destructive. That kind of thing can happen. Okay? All right, so we're going to do a class video for this day as well that involves solving a Wiley Plus problem for this kind of situation. That's all, though, for this video.